So I have actually, let's share my screen. So, yep, okay. I have actually put up on the Dropbox link, which Daniela has provided me with, all of the teaching materials I'm going to use today, and also tutorial 10 and the worksheet, which are the tutorial case for the Tesla car. Now I've got this on Dropbox myself, and tutorial 10, there is a worksheet which goes with the files. It's relatively self-explanatory. It's intended as a starting point for my students to do their own exploration, and basically there's the description of the Tesla car itself and how it's set up, and a description of the all-run file, with the intention that you understand what's going on and can pull it apart and change things as appropriate. And for the benefit of my students, there are a lot of suggestions here as to things they can do, and maybe which you would like to do if you choose to run this particular case, in terms of investigating, going beyond the all-run case. Because for my students, I don't want them to just type all run and then write up the results. I want them to actually do their own CFD. That being so, I asked and was allowed to change my topic somewhat, and I happen to have up my sleeve, as it were, a presentation and some tutorial files to do with turbulence modelling, which I used last year at the International OpenFOAM Workshop, and also for some teaching I did at the Politecnico di Milano, and which are therefore much more up to date. And the slide set, although I've actually altered it somewhat to accommodate some new information, to change things somewhat, the slide set was still reasonably up to date. So I've got some slides which I've put up here. UCL LES2 is this slide set. There are a number of case directories here associated with what I'm going to do today. And in particular, I've added another one of my tutorials, tutorial 7, which I hope to get to. And tutorial 7 is a case of, an example of calculating something called the Taylor-Green vortex using large eddy simulation. I will come to that though, because I wanted to start off and work my way up to that from fairly basic material. And this does mean that this is quite a good case to use here. I always am slightly concerned as to whether or not I'm pitching things to the right people in the audience. Daniela's polling this morning was very interesting, and obviously there are a number of people who hopefully have hung around for the session this afternoon who are well versed with OpenFOAM, at least running it, but also a fair number of people who are maybe beginners, just starting, and so forth. And this particular training session starts at a very basic level, eases you into turbulence modelling, I hope, but also contains some examples of runtime programming and things like that, which I hope more advanced members of the audience might find quite useful. Looking through the schedule for Friday, I noticed that there is actually a tutorial session on programming in OpenFOAM. So even if you're not currently up to speed with writing code in OpenFOAM, maybe you can attend that session on Friday and then come back and have another look at the session today, and it will make more sense at that stage. So what am I hoping for? Well, I'm hoping to describe and indeed demonstrate the use of some of the turbulence models available in OpenFOAM. And I'm going to include RANS models as well as LES and DES, detached eddy simulation models there. And I'm going to provide some tutorial examples here on a standard backward facing step, but also this Taylor-Green vortex, and take you through some of the setup of these cases, and also demonstrate some useful commands, particularly the command line system for post-processing and things like foam info for interacting with the code, with your model, and getting the most out of it. And then, as I mentioned, I also want to do a little bit more advanced material, in particular function objects, certain function objects, which are useful for running RAND simulation, for running LES and so forth, and a certain amount about how to code things like user-defined boundary conditions and so forth. I've mentioned this backward-facing step. Now you're probably all aware that in the tutorials in the distribution there is a backward-facing step case which shows up several times. In common with all of the tutorial cases which come in the distribution, there's absolutely no real attempt to describe what's going on or how it works. It's just some case files and an all run file, and you type all run and watch things happen. I don't like that, so I try and build tutorial cases which have a degree of explanation and something to back them up. And in this case, I've managed to find some experimental data, actually from a couple of years ago, published in Water Science and Engineering for, well, it's actually numerical simulation rather than experimental experiment, but it's a well-defined example of a backward-facing step flow, so I based my tutorial example on that. And as I say, I've provided the case files for the RANDS case, so the Epsilon case, and these are backward BF step and BF steps CFV, and I'll explain the difference later there. And I've also set up, and we'll show you, a more complete large eddy simulation case for the whole thing. And leaving myself rather open to questions on this. It works, or as I've tested it, and I've managed to run it using OpenFOAM version 7. It will probably work with other variants of the foundation case, and with modification with, for example, the OpenCFD branch of the code as well. But obviously there are subtle modifications in the different branches, and at least some of the of what I'm going to show you here is not so much telling you what works in a particular branch, but indicating how you might be able to find out what's available in the branch of the code you're trying to use at the time. One of the challenges we always face with OpenFOAM is converting from one version to the other and upgrading the case and so forth. So here's our backward-facing step geometry, and it's quite a long domain here. I reckon it's about 2 meters in length in total. The total width here is 10 centimeters and the step height is 5 centimeters, so it's a 1 to 2 step here. As I say, the case here from Wang and his collaborators is a numerical simulation, and he and I are using similar resolution meshes here. So X along the streamwise direction, Y normal to the top and bottom faces, and Z, when we come to do the LES case, is going to be the spanwise direction. So our resolution nx by ny on the expansion part is 210 cells in the streamwise direction and 40 cells in total normal to the walls. And for the LES case, I then expanded that by 32 cells in the spanwise direction. So that's my geometry there. Now, I'm actually quite proud of this. I really like mind mapping things. I find this is a good way of organising my thoughts. So in preparation for this last year, when I used this last year, I sat down and mind mapped the turbulence models in OpenFOAM. I actually used to have a vague mind map, but it wasn't a very good one, so I thought it was a good opportunity to update things. So here's my mind map of turbulence modelling in OpenFOAM, and I'm sure we're all familiar with the basics here. We can model turbulence, well, not just a model, but full simulation gives us direct numerical simulation. Reynolds or ensemble averaging gives us RANS models, of which there are eddy viscosity examples such as standard K-epsilon, but also more sophisticated models which are based on modeling the whole Reynolds stress tensor, and these can be either in algebraic form or in terms of a differential transport model. And conversely, the alternative averaging process we know of we use is a volume averaging, a filtering process, and that gives us our LES models. And again, we can further subdivide those into algebraic models such as Smagorinsky and transport equation models such as K equation models. And then the overlap between RANS and LES is where we blend the two to give ourselves detached eddy simulation, or whatever we choose to call that. There are lots of different descriptions here, but they all basically refer to a turbulence model which switches between a RANS version in near wall areas of the flow and something related to larger dissimulation in the free stream. And within OpenFOAM, there are a number of examples there. This is one area where there are very significant divergences between the different branches, depending on what has actually been implemented in any particular branch. But there's a whole family related to the Spalat-Almaraz model, which was originally an eddy viscosity model, but can be run as an LES version as well. And also another branch in terms of K omega, which once again was originally an eddy viscosity model, but can be used as a detached eddy model. Now, the basic codes here are either incompressible or compressible, and depending on whether or not we want to run steady state or transient, we may be using some version of simple or some version of piezo. So simple foam is our basic steady state simulation code using the simple algorithm, semi-implicit method for pressure-linked equations, whilst for transient flow cases we use the piezo algorithm in the form of piezo foam, and that's what we programmed with when I was back at Imperial in the 1990s, but in more recent times, and to most of the audience this will be old hat of course, pimple foam is a blend of simple algorithm and piezo algorithm. It's a time-stepping algorithm similar to piezo, but with internal iteration and under relaxation in every time step, similar to simple. And the net result of this is we can run much larger time steps using this pimple algorithm. I tend to use and teach using incompressible cases. There are, of course, compressible equivalents for all of these in the OpenFOAM library. So if you're doing compressible or sonic flows, then you're likely to be using a similar code, but based on a variable density here. And in all of the branches, the different turbulence models are available. They are either incompressible or compressible. I'm going to focus on the incompressible versions. And I actually took this out of the presentation, but in the programming here, we use a virtual base class and derive models from that. And the upshot of this is at runtime, you can easily swap between them. And you're all, I'm sure, familiar with how this works. We have a, I'll jump forward I'll come to it later, but we have a turbulence dictionary which contains all of the switches to switch between the different models. Now, this slide is one of the more important ones, finding out more. And this is basically what I did to construct my turbulence models framework, mind map here. I went through and dug through the code. Now, you get the code in the distribution, so you can go in there and list the files and open the files and look at them. But it's far easier these days to make use of some of the command line interface commands here. And one particularly good one is list turbulence models. And so if I want to find out about what's available in a particular OpenFOAM code, so say simple foam, I can ask to list turbulence models, and that's what I'm going to do here. So remember the OF7, so I'm running OpenFOAM 7, so simple foam. This is the point of course at which you find I can't type very well, so I shall be going backwards and forwards. List. There we go. And this has very nicely listed all of the turbulence model options I can choose to run with simple foam. And you can see, first of all, I can switch between LES, Reynolds averaged simulation, and laminar. Within the RAS models category, I've got a wide range of well-known and some not so well-known models here. And then in the LES models, I've got all of the LES models like Smagorinsky, Whale, dynamic K equation, but also it lists the detached eddy simulation models as well. So that's told me what I've got. What's in individual ones? Well, another command which is quite useful here is one called foam info, and this can be used to extract the information about a particular model. So foam info q zeta, for example, will return the information which is available in the header file for the q zeta model. If you know a bit about programming, you'll know in C++ we have C files which contain the code itself and .h files which are our header files. And inside the header files for the different classes, there is information about the individual classes. So for a turbulence model, there is information here about the turbulence model which has been implemented in terms of what it is and link or references to papers describing the implementation or where it's come from. This information can be extracted using deoxygen to give the manual pages, and if you look online you may well have seen it there, but it can be easier just to use this foam info command to extract the information. I noticed when I was looking through this that quite a number of these files in fact contain references to a particular online documentation from a guy called David Aspley in Manchester. This seems to be a good reference for a lot of the models which have been implemented in OpenFOAM. There's a description of what they are here and details of the physical model and mathematical modeling which has been implemented here. Okay, I might add simple list turbulence models and things like list boundary conditions and foam info can be used to extract information about other aspects of the library. So I've mentioned list boundary conditions as another command, which will give you a list of possible boundary conditions. And foam info, for example, you can use to find out about different viscosity models, for example. Similar sort of thing there. You can also use the command foam search with a little bit of practice to list the models used in the tutorial. These are the tutorials provided in the installation. So foam search the foam tutorials. Properties RAS model. Hopefully I've got that typed right. What this is going to do is it's going to search through the foam tutorials directory in the file marked turbulence properties for entries in the sub-dictionary RAS model here and just list them. That's unfortunately less useful than you might think, because all it's actually done is to return the keywords in the different dictionaries. It hasn't even told me which files are being referred to here, but it has at least given me information about what turbulence models are used in these different tutorial cases. So I can go back, and if I am interested, for example, in the Launder-Sharma K-epsilon model, I know there must be an example of it somewhere in the installation files. And I've listed here in my slides a very brief overview of the main models available in OpenFOAM. Not all of them. I stripped out the Reynolds stress models because they're really quite complicated, but we have implementations of the standard K-epsilon model and its RNG and realizable variants, also K-omega and K-omega SST, the Spalart-Almaras model, which is frequently used for aircraft calculations, and one which I was aware of but hadn't really had an opportunity to look into in much detail, the V2f model, which is a modification of a basic eddy viscosity model, but to account for anisotropy in the turbulence. So let's have a look at this. Here is my case directory for standard backward facing step. And if we go, we're looking at physical properties, so they come into constant, and in constant you can see there is a file here called Turbulence Properties, and if I open that, it's a standard dictionary in which we can specify that we're running a Reynolds average Navier-Stokes problem here, and a sub-dictionary here enables us to specify which model we're running. We're activating turbulence for it, and at the beginning of the run, I'm going to ask the simulation to print out the coefficients. Now, inside the implementation of the K-epsilon model are the standard values for the coefficients, all 5 of them, which you probably won't have to change, but if you have to, or you want to try with that, you can in fact overwrite that by including another sub-dictionary here. You'll notice the name here. I'm using the K-epsilon model, so I'm providing a sub-dictionary called K-epsilon coefs to specify the necessary coefficients for that particular model. And Turbulence Properties Dictionary enables me to select which turbulence model I'm going to use. That being so, I've also got polymesh in here, and I can run block mesh in the usual way, and because it's two-dimensional and quite a small case here, this is a very simple and quick run to do here. And I set it up to run using simple foam. So let's have a look at the settings for that. So in here, FV solution here specifies the different solvers, and I'm using algebraic multigrid, which is standard and quite fast here, and I've set it up with simple, and residual control enables me to stop the simulation once it converges to a level of 10⁻⁴ on pressure velocity, and any of my turbulence parameters or files that I'm dealing with here. This notation, by the way, is a form of input expansion. Forget what it's called, but it enables me to specify K, epsilon, and I could include here, if I wanted to, omega, if I was going to be solving for an omega field, and it specifies all of those are going to use a value of 10 to the minus 4 for the residual control. And again, under relaxation factors for all of these are specified here. Similarly, FE schemes here, as we probably all know, this enables me to specify what differencing schemes, what interpolation schemes I'm going to use. And you'll see I'm specifying this here. I do this exercise with my students. I do it for the K epsilon model, and then ask them to change to run using K omega, which is a good practice for them to do. Let's run this. So simple foam. Yeah, there we go. It's all running very nicely, and you can see that it converged in 222 iterations. We don't really have the concept of an iteration in OpenFOAM, which possibly is a little bit silly. So instead, we run this as a time step, and I like to set the time step here to be 1. So my time here is just my iteration number in my simulation. And you'll see the initial residual, which is what we are monitoring in our simple loop here. That's being printed out here, and once those initial residuals drop to less than 10 to the minus 5, then at that point our simple solution has converged. And we should be able to, first of all, let's have a look. Here we go. It printed out, it saved the file at 222 iteration here, and I can run parafoam in order to post-process the results. That. So as you can see, this is a 2-dimensional case, so it's 1 cell thick. I can put in the cell boundaries to give you some idea as to what my mesh resolution is like here, and I can also read in the necessary information. Let's bring in all of the volume fields here, and since it's 2-dimensional, I might as well represent this on the surface here. So for example, my velocity looks like this. And you may or may not be aware of the difference between the U as a point here and the U as a box here. U as a box here means display the cell center values. So if I do that, you will notice a very blocky representation here. What it's basically done is to color each cell here according to the cell center value. That can be quite useful if you're trying to track down what your simulation is actually doing, because these are the calculated values you're getting out of the simple loop. But if we want to present this in a rather nicer value, we instead use the point value here, which interpolates the data onto the vertices, and then based on that paraview can do a nice smooth interpolation on the data. So you have to remember this is an additional level of interpolation, but it looks a lot nicer as a result there. Okay, I'll close that and let's go back to the slides. Presentation. I should possibly just check to see if anybody's got any questions. Yes, I'm sure. The Dropbox is the one which has been provided to me by Daniela. I presume she'll be able to put up a link to it either now or at some point in the next 3 days. That would be great. Thank you very much, Daniela. I only uploaded them half an hour ago anyway, so it's entirely my fault if they're not there.
No, just we will fix this later, can be after the session. I think maybe there was a problem because in the folder there are no files in there. So
sorry.
maybe when I share,
it's probably my fault. As I say, I only uploaded them half an hour ago. I can see them there, but maybe I did something wrong. Anyway,
I think it was my fault because I set it up bad at the beginning, and well, we discussed this after, but
we will get back to it. You will get all of the files by the end of the week, I'm sure.
Thank you.
I've included a certain amount of information here about details like the wall modeling, for example. Wall modeling enables us to run with a coarser near wall mesh by using our physical knowledge of the properties of flow in a boundary layer. And the standard implementation assumes that the boundary layer, the first layer of cells, incorporates the log law region of the boundary layer, and so specifies velocity and turbulence profiles based on the logarithmic formula for the near wall flow. More recently, you can have flexible wall modeling, which extends into the laminar region. It checks the local y plus value and switches between logarithmic values and quadratic values based on whether or not this is the logarithmic turbulent flow or the laminar sublayer there. And in OpenFOAM, the basic wall boundary condition is implemented on the NUT field, the turbulent viscosity field, and there's a range of wall functions available. And once again, this is an area where the different versions of the code do things very slightly differently. NUTK wall function is the standard one here, but there are a number of other ones here. In particular, I think Spalding wall function is the switchable one. I forget exactly. If you are using epsilon, omega, and k, you may very well want to use, the low Reynolds number versions are k low Reynolds wall function. Sorry. If you are using a RANS model with k, omega, and epsilon, you are very likely to want wall functions for those as well, and they are implemented. Now, in terms of the inlet boundary conditions, we are specifying these for the velocity, for k, and for epsilon. Unfortunately, normally we don't know the actual field values, but in CFD in general, we tend to use rules of thumb to specify these. And you can sit down and calculate those with pencil and paper, but OpenFOAM does provide the usual convenience functions. So there's a turbulent intensity kinetic energy inlet condition, which implements it based on the turbulent intensity I, and there are equivalent things for epsilon and for omega based on specified mixing lengths. And if we go back to my directories here, my case here, and if we look at the starting files here, you will see that in NUT I have correctly implemented NUTK wall function. And in things like the K file, hopefully I'm right, yeah, I'm using KQR wall function to implement the wall functions there. And for the velocity, I am indeed using here, now I'm just giving a fixed value inlet there, but for K, for example, I am using here turbulent intensity kinetic energy inlet with an intensity of 20% for my calculation here. Carrying on, and I'll go back to the presentation here. I include some information about V2f as a turbulence model in case you haven't come across that beforehand, but I'm going to jump over that because I wanted to say a little bit about useful post-processing here. And once again, there are various quantities which are useful to be able to calculate, often as post-processing activities, and we can do this using the command line interface. Now, a lot of this needs us to have access to the turbulence model. And so the exact form of the command line interface command is based on SimpleFOAM, because you need to have access to SimpleFOAM to have access to the correct turbulence quantities. But we can use this command line interface command to post-process and to extract various pieces of information. We can extract a turbulence intensity quantity, a wall shear stress quantity, and the Y+ value, which of course is something which is really useful for our wall, something we need to know for our wall modeling. So let's have a go with that. So SimpleFOAM post-process func Y+. There we go. That was pretty quick. It's printed out some of the useful information, and in particular, it has given us information about the Y+ values on the different wall patches, which are the top, the step, and the base. Is giving me minimum and maximum values and average. And of course, for our logarithmic law of the wall, we want our minimum value to be at least 11.6, and our average should probably be 25 to 30 or something like that. And I'm fairly confident I'm happy with those values. If we actually look at what this has done to our simulation, you'll notice that we've now got a file here, Y+. It's actually generated a Y+ field, which we could display using ParaView. And it's also given us a directory post-processing, which gives us the actual values as data files. So if you forgot to save the output log file here, the information is stored where you can make use of it. Okay, that's our very basic RANS backwards facing step case. At that point, I decided I'd get a little bit fancy, because in Wang's original paper, they've actually specified the actual mean flow inlet profile, and they fit this to a function, which is an exponential function, a two-piece function, which gives an inlet profile looking like this. So this is the experimental data they based their calculations on, and for their simulations, they've actually used this inlet profile. So far, my simulation doesn't do this. It just has a uniform inlet velocity. So I thought, hey, I want to change that. I want my OpenFOAM simulation to be at least as good as whatever Wang was using for his code. So I want to put in a user-defined inlet condition. And we can do this using a new type of boundary condition called a coded boundary condition. And a few years ago, this was implemented in a number of the versions of OpenFOAM. It's a particular type of condition called a coded fixed value. And basically what this does here is it says expect some code. And the code is specified in C format between hash open brackets and hash close brackets like this. So this is our basic coded boundary condition here, and it says take what's between these here as C++ code, compile it, and try and run it. And the redirect instruction here gives our boundary condition an actual name, and inside this I have specified some code, which those of you who have done some coding in OpenFOAM will find relatively straightforward to understand. If you haven't, I will try and give you an explanation here, and if you follow the coding session on Friday, hopefully that will give you a bit more information. It's actually quite straightforward. I like to see OpenFOAM basically as a programming language like MATLAB for doing CFD with. So this is the difference between BF step and BF step CFV. So coded CFV, coded fixed value. So in this case, in my 0 time step directory, in my U file here, I have introduced my coded boundary condition. Now, in order to code this profile, obviously I need to know how far away from the boundary my face value actually is. So my inlet is a patch, which is a collection of boundary faces with values at the face centers. So I need to work out the Y value of my face center, calculate this for either one side of the boundary or the other side of the boundary, so it's switching between the two of them, and re-implement that into the code there. So that's exactly what's going on here. My basic object here is a patch, so I want to give myself a reference to the patch which I'm using here. Having done that, I can ask for the cell center values. Now, that's a slightly odd way of putting it. The cell center, of course, now it's a face, so this gives me the face centers of the different faces making up the boundary patch. This is a vector, or rather it's a vector field, because it's the position in space of the center of each face in my patch. And I'm also giving myself I'm naming the vector field I'm processing here field here. I'm then setting up my different parameters M and U here and H according to the values I know here. And then I need to loop over every face in my patch, work out the x component of the velocity and put that into my vector. So for all entries in this CF vector field, which are the centers of my faces here, I'm going to loop over them. I'm going to find the Y component of the position. I'm calling that Y. Why am I doing that? Well, at this point I've had to hard code it because I've had my patch is not centered on 0, it's actually off center, so I've had to take account of that off centering there to get the distance away from the wall in each case, and then based on whether or not I'm on this side of the patch or this side of the patch, I can calculate each of these expressions and plug them into my vector in each case there. Having done that, I can then run the calculation. So let's do that, OF7. Here we go. And you'll notice the first thing it's done is to tell me it's doing a certain amount of compilation. There we go. Whilst it did this is it compiling my new boundary condition. Whilst it did this, it generated this new directory dynamic code. And when it started running here, it was using my new boundary condition. Now, I noticed from the question and answer, I've got a question from somebody saying, there are so many options in RANDs, how do I make a choice? You are dead right, there are so many choices here. And this is where our expertise as CFD practitioners comes in. And the honest answer here is go to my lectures on turbulence modeling in my CFD course, and I spend about 4 hours explaining how to make what the different choices are. K-epsilon is a very basic standard model which works for a lot of cases, and so it's a good one to start with. So it's the starting point very often for RANS modeling, but it's not necessarily the end point for RANS modeling. It has various deficiencies, which when you learn about RANS models, you learn about the deficiencies here. And if your case that you're trying to simulate falls into one of the categories that K-epsilon doesn't do very well, that's when you might very well want to switch to an alternative. So, for example, it's known that the K-epsilon model equations do not work very well for rotating flows, but there is a variant called the realizable K-epsilon model, which has been developed precisely to do that particular case. So you've got a lot of stuff to learn about, but the honest answer is this is why we study these models, in order to be able to make an informed choice. And also this is why we validate our CFD simulations before we trust them. So we find data from our backward facing step, and we check that our simulation results are coming out correct. Now, we've got 10 minutes to go, and as usual, I'm running out of time here. I've basically got two things I can do here, because I've set up, I talk a bit about large eddy simulation here, and I have set up two cases to show you in large eddy simulation. I probably only got time to really do one of them. So I'm going to just mention the backward facing step case first of all, and then talk about the Taylor-Green vortex. Backward facing step case. Lo Feng, you wanted to say something about choices in RANS?
No, did I raise my hand?
Okay, fine.
Oh, sorry.
Sorry, you've got, yeah, fine, okay. Okay, right, well, the two cases I've got to show you here are a version of the backward-facing step case, which I've set up to run using LES, and there is also the Taylor-Green vortex case here, which is Taylor-Green vortex. Okay, so backward-facing step first of all. Now, for the RANS case, I was able to run this in 2 dimensions and steady state. You can't do that for LES. LES, large eddy simulation, divides the flow into the big eddies, which are explicitly, the large-scale eddies, which are explicitly simulated, and smaller subgrid scale structure, which we throw away and we replace with a subgrid scale model. Since the larger eddies are part of the turbulence, they are 3-dimensional and they are transient, so our simulations also have to be 3-dimensional and transient. So that means either piezo foam or pimple foam, and it means running the thing in 3 dimensions. This also means this takes a long time to simulate, and I spent quite a long time getting from the 0 time step directory to the 15 time step directory, just setting the thing up, because it takes a while for the turbulence in the flow to develop. And then if you run it just straightforwardly, you will notice that the start point for my calculation here is 15, and if you run it from that point onwards, it will generate the results from 15 to 30 on this. That does, of course, mean that I can show you some of the results here. So if I open this, go to the 15 time step and read in the files. Here we've now got a domain which is three-dimensional. I've got something like 40 cells across the domain here, and that means that my full structure here is itself three-dimensional. Now, one of the things I talk about two things here, one of which is how we actually post-process the turbulence in this particular case. Now, we are explicitly calculating the large scales in the flow problem here, and we want to identify the vortex motions we're seeing there. And there are a number of ways we can do this. For example, vorticity is related, the vortex structure is related to the vorticity in the flow, which is the curl of the velocity field. And so we can evaluate this quantity entropy, which is a half of the magnitude squared of the curl here. And there's a post-processing command which can be used to generate that quantity. There are also a couple of quantities, the Q criteria and lambda 2, which relate to what are called invariants of the strain tensor. So we can calculate the gradient of the velocity, and that's a 3×3 matrix, and it's a tensor. So it has what are called invariants, which are quantities of the tensor which don't change if we change the basis function. So if we rotate our axes, these quantities remain the same. This means that they make very good quantities for examining aspects of the tensor itself. And for example, the second invariant, Q, if Q is less than 0, we've got a region of large strain. Whereas if we've got Q greater than 0, we've got a region of high entropy, I of vortex. So that enables us to identify our vortices. The other thing we can show is that a structure is a vortex if at least 2 of the eigenvalues are negative. And once again, this criteria, lambda 2, is something we can evaluate in our simulations. And again, we can run these quantities and post-process the results. I'll do that separately. 7. So let's do Q value post. And that's going to calculate this Q parameter for each of my saved time steps here. The other aspect of this is the flow is transient, but very often we want to examine the averaged flow, and that means that we need to calculate averages. Now, I could read in these saved time steps, add them up and divide by 5, but that would be a very coarse averaging. I could save every time step, but I don't have enough time, the disk space. Instead, what we tend to use is a function object. There's one called field average, which does a running average of these quantities. And it will give you the arithmetical mean and the square of the basically variance here as a running average for each time step in our calculation. There's some information here about what the different switches mean, but I've actually done this in this case, and you'll see that there are, in addition to the U field here, which is the instantaneous velocity, there's also a mean value there. Now I'm almost out of time, so I will just finish by post-processing and showing you some of this. So let's put through a slice through the domain here in the Z direction like that. And we can look at various quantities on this here. So we can see here instantaneously that this is our instantaneous velocity field, and it's transient. It's got much more structure in there, but I can also read in the mean velocity here, I can post-process. I can now display this mean velocity, yes, I think I can. I should have been able to. Try that again. For some reason which I don't understand, it's not showing up. But what is showing up is my Q criteria, and that's correctly identifying the location of my vortices here. As usual, when I'm doing things with 100 people looking over my shoulder doing this, something goes wrong and I can't work out what, but the U-mean field is there, and it's something I should be able to post-process for you. Probably something to do with the fact that these are average values. Anyway, I'm going to have to stop at that point. I will just remark that the last part here I had was some discussion of the Taylor-Green vortex, which I keep wanting to do, but keep running out of time. But for the Taylor-Green vortex case, I have actually provided my tutorial notes, which actually describe the setup of that particular case in some detail. So, I've got a couple of questions. Yes, the LES mesh there is quite coarse. I haven't really done this case in any great detail here. The usual rule of thumb is that you want 70 to 80% of your turbulent kinetic energy in the flow being resolved. The problem with that, of course, is that's an a posteriori way of doing things. So you very often run a RAN simulation or something like that to get some estimate of the resolution necessary and then adapt the mesh based on that. But it is something of an art form to establish the correct fineness of your LES calculation. And to be honest, one of the great criticisms of LES is that it does give a very strong linkage between the mesh and the turbulence simulation method, which isn't necessarily the most beneficial thing there. Got another one. What do you think about developing fields with a RAN setup prior to switching to an LES simulation? That's exactly what I did, actually. I took my RAN simulation, turned it into 3D case, and then switched over to LES, basically. It takes a long time for the turbulent field to develop in LES. You can find you're having to do a very large number of time steps to get the simulation running, and anything you can do to give yourself a shortcut of that is very definitely beneficial. Recently, I saw many papers on subgrid scale which calculated with the help of neural network, which are then combined with LES. Please give your views on this direction. I think it's a fascinating idea. I actually ran a project about 10 years ago where I used genetic algorithms to optimize the coefficients in models, and that was very interesting and educational. I would been wanting to try to use neural networks in this manner for a while. I just haven't been getting around to do it. That's fantastic, but I think it's a very interesting direction for turbulence modeling to take here. Ah, yes, U-mean wasn't shown because I've calculated some further time steps. Yeah, of course, yes, you are absolutely right. I am being stupid. Let's go on to U-mean. There we go. Yes, thank you very much. You are absolutely correct. I think I may have to get rid of that. Let's go back. Tools, filters, slice, Okay, so here's my mean flow. So here's my instantaneous velocity field, whereas here is my mean flow. My mean flow is much more smooth there. Thank you, Farhad. Award yourself a pat on the head. So obviously I just did that as a test to see who was actually awake, and obviously I'm not awake. Anyway, I think I've run out of time there. I've probably run into the next person's session, for which I heartily apologise. I guess I will duck out